Welcome to IQriously. Get comfortable. Take a slow breath. Tonight we are going to talk about something you have almost certainly sat inside, or stood next to, or driven past thousands of times in your life. Something so familiar that most of us have never stopped to ask how it actually works. A machine that turns the controlled explosion of a small amount of liquid into the movement of a vehicle weighing over a tonne. A machine invented in the 19th century that still powers the majority of the world's vehicles today. The internal combustion engine. There is something almost meditative about the way these machines work. The same sequence of events, repeating thousands of times every minute, for hours, for years. Suck, squeeze, bang, blow. 4 beats. Like a very mechanical kind of breathing. By the end of tonight, you will understand exactly what is happening inside that familiar sound. The rumble and purr of an engine warming up on a cold morning. There is nothing you need to do. Nowhere you need to be. Just listen. To understand the combustion engine, we need to start somewhere unexpected. We need to start with fire. Fire is a chemical reaction. When a fuel, wood, coal, petrol, anything combustible is combined with oxygen and given enough heat to get started, the molecules of the fuel react with the oxygen molecules in the air. They break apart and recombine into new molecules, mostly carbon dioxide and water vapor. And in the process of that recombination, they release energy, heat and light. This is what fire is. A very rapid process of molecules breaking and reforming, releasing the energy that was stored in their original bonds. The question that engineers have been asking for centuries is a simple one. Can we capture that released energy and use it to do useful work? Early answers focused on steam. Heat, water. Water boils. Steam expands. Use the expanding steam to push a piston. The piston moves a shaft. The shaft turns a wheel. The steam engine which powered the Industrial Revolution was this idea made practical. But steam engines are large. They need a furnace and a boiler and a constant supply of water. They take time to build up pressure. They are not, in short, something you can fold into a vehicle and drive down a road. The dream, through most of the 19th century, was an engine that could create its own power from a small supply of fuel carried with it. An engine that didn't need an external furnace. An engine that burned its fuel internally. The internal combustion engine. The first practical internal combustion engines ran on coal gas, the kind that was piped into buildings for lighting. A Belgian inventor named Etienne Lenoir built one in 1860. It was unreliable, inefficient, and barely more powerful than a horse. But it worked. It proved the concept. The gas entered a cylinder. A spark ignited it. The expanding gases pushed a piston. The piston moved a shaft. The shaft did work. The basic idea was sound. What it needed was refinement. That refinement came from a German salesman named Nikolaus Otto. Otto had no formal engineering education. He was a traveling merchant who sold sugar, tea, and kitchenware. He encountered Lenoir's engine and became obsessed with improving it. He spent 14 years working on the problem. He and his business partner built a factory in Deutz, near Cologne. 2 brilliant engineers joined the company, Gottlieb Daimler and Wilhelm Maybach. And in May 1876, after a decade and a half of effort, Otto built something that would change the world. A 4-stroke engine. He called the operating principle the Otto cycle. It is still, today, the operating principle of the majority of petrol engines on Earth. The four-stroke cycle is the heart of the modern combustion engine. Let's walk through it slowly and carefully. The key component is the cylinder. Inside the cylinder sits a piston, a tight-fitting disc that can slide up and down within the cylinder walls. Connected to the bottom of the piston is a connecting rod, which is attached to a crankshaft, a rotating shaft that converts the up and down motion of the piston into the rotational motion needed to turn wheels. At the top of the cylinder is a small space, the combustion chamber, where the fuel and air will be mixed and burned. And into that chamber open two valves, an intake valve through which the fresh fuel air mixture enters, and an exhaust valve through which the burned gases leave. Now, the four strokes. Stroke 1 is the intake stroke. The piston begins at the top of the cylinder. The intake valve opens. The piston moves downward. As it moves down, it creates a low-pressure zone in the cylinder, just like pulling back the plunger of a syringe. The pressure difference sucks a mixture of air and atomized fuel down through the open intake valve and into the cylinder. The intake valve closes. The piston is now at the bottom of the cylinder, with a cylinder full of fuel air mixture above it. Stroke 1 complete. Stroke 2 is the compression stroke. Both valves are now closed. The piston moves upward. As it compresses the fuel air mixture into the much smaller space of the combustion chamber at the top of the cylinder, the mixture gets hot. And more importantly, it becomes much more reactive. Compressed gases are more energetic. A compressed fuel air mixture will release more energy when ignited than an uncompressed one. The compression ratio, how much the mixture is compressed, is one of the most important numbers in engine design. A higher compression ratio means more power and better efficiency. Modern engines typically compress the fuel air mixture to somewhere between 8 and 12 times its original volume. The piston reaches the top of the cylinder. The mixture is compressed, hot, ready. Stroke 2 complete. Stroke 3 is the power stroke. This is the only stroke that actually produces power. The other three strokes are, in a sense, preparation for this moment. Just as the piston reaches the top of its compression stroke, the spark plug fires. A tiny electrical spark across a gap of less than a millimeter ignites the compressed fuel air mixture. The mixture does not explode in the dramatic sense. It burns rapidly, very rapidly. In a fraction of a second, the burning gases expand enormously. They push outward in all directions. The cylinder walls and the top of the cylinder resist the pressure. The piston does not. It is driven downward with tremendous force. That force travels through the connecting rod to the crankshaft. The crankshaft rotates. Power is produced. This is the bang in the informal mnemonic suck, squeeze, bang, blow. The piston is slammed down by the expanding combustion gases. Stroke 3 complete. Stroke 4 is the exhaust stroke. The power has been extracted. The cylinder is now full of burned gases, carbon dioxide, water vapor, and various other combustion products. These need to be tiered out before the next intake stroke. The exhaust valve opens. The piston moves upward again. It pushes the spent gases out through the exhaust valve and out of the engine, eventually through the exhaust pipe and out into the atmosphere. The exhaust valve closes. The intake valve opens, and the cycle begins again. Suck, squeeze, bang, blow. In a typical car engine at highway speed, this cycle happens about 3,000 times per minute in each cylinder. Not once a minute. Not once a second. 50 times a second. and a typical car engine has 4, 6, or 8 cylinders, all firing in sequence. The mechanical ballet of their coordinated strokes is what produces the smooth, continuous rotation of the crankshaft that eventually turns the wheels. Now, let's zoom out, because the cylinder and piston are only part of the story. Around them, supporting them, managing them, is an intricate system of components that together make the engine work. Let's meet some of them. The fuel system. In older engines, a device called a carburetor mixed fuel and air in the right proportions before the mixture entered the cylinder. Modern engines use fuel injection, precise electronic systems that spray the exact right amount of fuel directly into the intake manifold, or even directly into the cylinder at exactly the right moment. The stoichiometric ratio, the chemically ideal ratio of air to fuel for complete combustion, is about 14.7 parts, air to 1 part fuel by mass. Too much fuel and the mixture is rich. It burns incompletely, wastes fuel, and produces more pollution. Too little fuel and the mixture is lean. It burns too hot and can damage the engine. Modern fuel injection systems adjust this ratio many times per second, responding to thousands of data points from sensors throughout the engine. The ignition system. The spark plugs are the ignition system's most visible components, the small devices that screw into the top of each cylinder and deliver the electrical spark that ignites the mixture. Each spark plug fires once per 2 rotations of the crankshaft, once for every complete 4-stroke cycle. At 3000 RP, each plug fires 1,500 times per minute, 25 times per second. The timing of the spark is critical. If the spark fires too early before the piston reaches the top of the compression stroke, the burning gases push against the still rising piston. The engine knocks and loses power. If the spark fires too late after the piston has already started moving downward, the gases expand into a growing space and the pressure wave is weaker, also less efficient. The ideal timing is just before the piston reaches the top of its stroke, giving the combustion process just enough time to develop full pressure at exactly the right moment. Modern engine management computers adjust the ignition timing continuously, compensating for engine speed, load, temperature, and the quality of the fuel. The cooling system. Combustion produces enormous amounts of heat. Without cooling, the metal of the engine would simply melt. Most car engines are water-cooled. A liquid coolant, usually a mixture of water and antifreeze, circulates through passages in the engine block, absorbing heat from the metal. The hot coolant passes through the radiator, the component at the front of the car, behind the grille where it is cooled by airflow. The cooled liquid returns to the engine, and the cycle continues. The operating temperature of a typical petrol engine is somewhere between 80 and 105 degrees Celsius. Hot enough that the coolant would boil if the system wasn't pressurized. Pressurizing the coolant raises its boiling point, allowing the engine to run hotter, which improves efficiency. The thermostat, a temperature-sensitive valve in the cooling circuit, keeps the engine at its optimal temperature. When the engine is cold, the thermostat is closed, and coolant circulates only within the engine, warming up quickly. When the engine reaches operating temperature, the thermostat opens, and the full cooling circuit activates. The lubrication system. Metal moving against metal at high speed and high temperature will quickly destroy itself without lubrication. Engine oil fills this role. Oil is pumped from the reservoir at the bottom of the engine under pressure to every moving surface that needs it. The main bearings of the crankshaft, the connecting rod bearings, the camshaft, the valve gear. Oil does not just lubricate. It also cools, carrying heat away from surfaces that the water coolant cannot reach. It also cleans, suspending tiny particles of debris and carrying them back to the oil filter, where they are removed. The oil filter is a simple but vital component. Without it, the abrasive particles created by normal engine wear would circulate with the oil and accelerate that wear catastrophically. This is why changing the engine oil regularly is not optional. The oil degrades. It gets contaminated. It gets thicker. And old, degraded oil is one of the fastest ways to destroy an engine. The exhaust system. The burned gases leaving the cylinder are hot, toxic, and extremely loud. The exhaust system collects these gases from all the cylinders through the exhaust manifold, runs them through a catalytic converter, and then through the muffler, called a silencer in British English, and out through the exhaust pipe. The catalytic converter is one of the most important pieces of environmental technology in the modern car. Inside it, precious metals, platinum, palladium, and rhodium act as catalysts. They cause the toxic gases from combustion carbon monoxide, unburned hydrocarbons, and nitrogen oxides to react with each other and with oxygen, converting them into less harmful substances. Carbon monoxide becomes carbon dioxide. Hydrocarbons become carbon dioxide and water. Nitrogen oxides become nitrogen and oxygen. The converter works only when hot, which is why most vehicle emissions occur in the first few minutes of a cold engine before the catalyst has reached its operating temperature. The valve train. We mentioned the intake and exhaust valves earlier, but we did not explain what opens and closes them. That job belongs to the camshaft. The camshaft is a shaft with egg-shaped lobes, cams machined onto it. As the camshaft rotates, driven by the crankshaft through a timing belt or chain, the lobes push against the valves, opening them at precisely the right moment in the cycle. The shape of the cam lobe determines exactly when the valve opens, how far it opens, and how long it stays open. Engine performance tuners spend a great deal of time modifying cam profiles to change an engine's characteristics. More aggressive cams can increase power at high revs at the cost of smooth running at low revs. Most modern engines have variable valve timing systems that can alter the timing of the valves depending on engine speed and load, optimizing performance across a wide range of conditions. Now let's take a step back from the components and ask a deeper question. How efficient is all of this, really? The answer is humbling. A typical petrol engine converts only about 20 to 40% of the energy in the fuel into useful work. The rest is wasted. Most of it as heat exhausted through the cooling system and the exhaust pipe. Some as friction, the unavoidable resistance of metal moving against metal, even with lubrication. Some as pumping losses, the energy spent pushing gases in and out of the cylinders. 40% efficiency at best. For every litre of petrol you burn, only 40% of its energy reaches the wheels. The rest heats the air. This seems wasteful, and it is. But it is also a consequence of the fundamental laws of thermodynamics. No heat engine, no engine that operates by burning fuel and using the heat, can be perfectly efficient. This is not an engineering failure. It is a law of physics. The theoretical maximum efficiency of a heat engine is determined by the temperature difference between the hot gases inside the cylinder and the cold gases leaving through the exhaust. More temperature difference means more potential efficiency. This is why modern engines run hot, higher operating temperatures allow closer approach to the theoretical maximum. Diesel engines work on the same four-stroke principle as petrol engines, with one crucial difference. There is no spark plug. Instead of igniting a compressed fuel-air mixture with a spark, a diesel engine compresses the air so much, typically 14 to 25 times its original volume, that the compression alone heats the air to the AE. Ignition temperature of diesel fuel. When diesel is injected into this superheated air, it ignites spontaneously. No spark required. This means diesel engines can run at higher compression ratios than petrol engines, and higher compression means better thermal efficiency. A good diesel engine can achieve efficiencies of 45 to 50%, compared to 30 to 40% for a typical petrol engine. This is why diesel became the preferred fuel for trucks, buses, ships, and any application where fuel economy over long distances matters more than smooth, responsive performance. The downside is that the higher compression ratios require stronger, heavier engine components. Diesel engines are heavier and more expensive to build than petrol equivalents. And the spontaneous ignition that makes them efficient also makes them produce more particulate matter, the fine soot particles that make diesel emissions a significant air quality concern in cities. Let's talk about something that most people who drive every day have never thought about: the flywheel. The crankshaft receives a strong push from the piston once per cycle during the power stroke. The rest of the time during intake, compression, and exhaust, the crankshaft is not being driven. It is being carried. If the crankshaft were connected directly to the wheels, the engine would lurch and stutter with every cycle. The flywheel solves this. A heavy disc attached to the end of the crankshaft, the flywheel stores rotational energy during the power stroke and releases it during the other 3 strokes. Its mass smooths out the pulses. The heavier the flywheel, the smoother the engine runs, but the slower it responds to changes in throttle. Sports cars have light flywheels for sharp throttle response. Heavy trucks have massive flywheels for smooth, consistent power delivery. The flywheel is also connected to the starter motor, the electric motor that spins the engine up to speed when you turn the key. Before electronic starters, you started engines with a hand crank. Early motorists developed a healthy respect for the possibility of a backfire. When the engine fires on the compression stroke instead of the power stroke, the crank can kick backward violently. Broken wrists were a genuine occupational hazard of early motoring. The gearbox. The combustion engine produces its best power and efficiency within a specific range of rotational speeds. Too slow, and it does not have enough momentum to complete the cycle. Too fast, and friction and heat become limiting factors. The gearbox or transmission matches the engine's operating speed to the vehicle's needs. In a low gear, the engine turns many times for each rotation of the wheels. The vehicle moves slowly but has enormous torque rotational force for starting from rest or climbing a hill. In a high gear, the engine turns fewer times for each wheel rotation. The vehicle moves faster, and the engine operates at the efficient mid-range of its power curve. The art of driving a manual gearbox is the art of keeping the engine in its optimal operating range by selecting the right gear for the speed and the task. Automatic gearboxes do this electronically, reading the throttle position, vehicle speed, and engine load many times per second and selecting the optimal gear. Modern automatic transmissions are often more fuel efficient than most drivers manage with a manual because they are not influenced by distraction, mood, or impatience. There is something worth pausing on as we reach the end of this journey through the engine. The internal combustion engine is one of the most refined mechanical devices ever created by human beings. For over 100 years, engineers have been iterating on Otto's 4-stroke cycle. Every component has been analyzed, tested, redesigned, and optimized thousands of times. Modern engines produce dramatically more power from a given displacement than engines of 50 years ago, while using significantly less fuel and producing vastly fewer emissions. The best modern petrol engines are mechanical marvels, tolerances machined to within thousandths of a millimeter, materials developed through decades of materials science, software systems making thousands of hours, adjustments per second. And yet, the fundamental idea is unchanged from 1876. A cylinder, a piston, fuel and air, a spark, suck, squeeze, bang, blow. 4 strokes, thousands of times per minute, year after year. The same patient, repetitive rhythm that has been carrying the world forward for a century and a half. There is something almost restful about that. A machine doing the same thing, over and over, with extraordinary precision, like breathing. Thank you for spending this time with IQriously. Rest well.